Hi, physics class. Do you remember that the last time we met, we were talking about launching we were talking about projectiles being launched horizontally and also up at an angle. And the last problem that we tackled was this one, where we had to figure out the horizontal and the vertical velocity. And then we even had to figure out that if it was going to be projected out for 3 seconds, how far away it would be. So we were able to find the range of it. Now we're actually given the two components, and we have to figure out the magnitude and the direction. So this is what we've been doing before with our vectors. And so let's read this. A football is kicked with a vertical velocity of 30 meters per second up and a horizontal cross velocity of 10 meters per second. Find the magnitude and the direction. That means find the velocity, the magnitude, and the direction would be the angle up from the horizontal. And so there's our picture. It's kind of out of whack. It should be taller than that. And r is a resultant that we'll use the Pythagorean theorem for. And the theta, we will probably have to use tangent because you can see that we've got the opposite side right here and the adjacent side here. So let's go ahead and try and find theta. So we'll use tangent to find theta and the opposite over adjacent. Okay, the opposite of 30 meters per second over 10 meters per second. And so we'll have to use our arctangent. I shouldn't have an equal sign in here, but I got it in there. So we'll have to use our inverse tangent, and we can find that. There we go. And that is 71.6 degrees up from the horizontal. That is theta that we just figured out. So it's up from the horizontal. There we go. Okay, so then now we need to find also the magnitude. We just found the direction, we need to find the magnitude, and we'll use Pythagorean's theorem. Remember, I've shown it to you written this way before too, where it's r squared equals x squared plus y squared. Well, I just went and took the square root of both sides also. And so here is our adjacent side and our opposite side, and we've got to square both of them. And when we calculate that, it's 31.6 is the total speed that it is going off of. So how would we report this? We would report it that it is 31.6 meters per second. Okay, meters per second, and it is 71.6 degrees up from the horizontal. So that's all of this is the answer, and this should have meters per second there. One more example before we move on to another concept. Okay, if football is kicked, oh, I'm sorry. Huh. Okay, one more sample. Here we go. A batted baseball leaves a bat with a velocity of 50 meters per second at an angle of 30 degrees from the horizontal. What is the horizontal and vertical component? So we're going backwards from what we did with the last one. This is more like our very first problem. So we probably better draw out our picture. Okay, and I'm going to ask you to solve this one and to pause the movie. I gave you a couple of hints up there, and so pause the video and we'll come back and talk about it. Okay, anyway, with the sign being for the opposite side, okay, the velocity is what you're calculating there. It is the opposite side is what you would need to find the velocity in the y direction. Okay, you would go and take the sine of 30 degrees, okay, times the 50 meters per second. And remember I said to plug it in the calculator this way, and you should get 25 meters per second. The cosine is for the adjacent side that is attached to the 30 degrees, but it isn't obviously the hypotenuse. Anyway, so the cosine is the adjacent over the hypotenuse, and so we'll have to take cosine of 30, and we'll have to multiply it by the 50 to get the velocity in the x direction. So 50 is how you should plug it into your calculator. 50 times the cosine of 30, and that would give you 43.3 meters per second. I hope you did well on that. You'll have to show me how you did tomorrow. Okay, let's talk about this. Notice that that the height and the length of the projectile, how are they related? Just even looking at this video, because we've got to assume that the ball didn't lose any speed, and so it keeps on going off at the same one. So if it was even at the same speed here, okay, notice that it's being projected at a lower angle, but it's got a longer range. Okay, here's a higher angle, and it's being a shorter range. So that's what we're trying to get to understand. And so we would do a PhET simulation. Hopefully we've already done that, and that would help us understand a few things. First, that it depends at what angle that you are projecting your projectile at. Okay, at different angles. The higher that it is, the closer it'll be from the original spot. The farther out, okay, up until a certain point, now we're farther is at a lower angle here, and now it's starting to get shorter again. There are some actual pairs here that is really cool to look at. I gave you this picture to draw from. Check it out. You will see that 75 degrees and 15 has the same distance, and that 60 and 30 has the same distance. So I have a question for you. What can you tell me about these pairs? Let me show you a picture here real quick. Okay, 75 and 15 has the same range. 60 degrees, being launched at 60 degrees and 30 degrees, now of course these are all the same speed, has the same range. And notice that 45 has one range here, and it is the longest distance. From our PhET simulations, you should have realized and came to the conclusion that 45 degrees is the longest range that you can project it out at. And so here's another diagram I saw, and so it'll give you the maximum distance when it's at 45 degrees, and we saw that several times with the projectiles lab on the PhET simulation. And but let's look back at these pairs here. Okay, what do they have in common? And I know that most of you are talking about this, and that you saw that both the angles that had the same range added up to 90 degrees. Amazing. 45, if you double it, guess what? You get 90 degrees. So that's pretty cool, and it does have a very true actual measurement like that, even with air resistance. So it kind of verifies what our PhET simulation did. Here's, remember this one? Anyway, there are horizontal and vertical components. We talked about that. And I want you to put this table on your formula sheet. It is so important for you to be able to do all of your problems right. And remember, we were talking about with this one, when a projectile is projected out, remember, it doesn't accelerate to the right. It doesn't accelerate to the right, and so its horizontal component shows that the velocity stays constant, okay, and that there is no acceleration in the horizontal direction. We know, of course, though, that projectiles fall at a faster rate as they fall. Okay, and so we know that they accelerate. In fact, they accelerate at 9.8 meters per second squared. And you can use these two formulas, but this one you need your acceleration 9.8 meters per second squared and time, and same with this one. But it's got one other variable in there, so this will help you determine which one of these two that you'll be using often. So let's go ahead and practice with one of these. Gee, it just skipped a whole bunch of pages here. Okay, a long jumper jumps horizontally from a ledge that is a height of 1.6 meters with a horizontal velocity of 6 meters per second. Where will she land? Okay, so we're trying to actually find the distance at the bottom, x. What we need to find is x, and we need a formula for it. And there's only one formula that's got x in it, and that's in that middle column on that formula sheet that we just looked at. And so to find that, we need velocity in the x direction. We got that, but we don't have time. We don't have time, so how could we figure this out? So we'll have to use a vertical component then to figure out time. And so we can do that with our vertical information that we have, because we do have how high that little ledge is. And so we know the acceleration due to gravity. Okay, we know that it's 9.8. Oh dear, this is just moving too fast. Hold on. And so with that in mind, we do know the height of it, but we do not know the velocity in the y direction. So we will have to use this top one to help us solve for time. So I've got another formula for you to think about here. Okay, that one you've even had this formula before on our formula sheet, but with that in mind, we need to solve for time. So that's going to have a square root involved, and I've got the formula written for you here. So you can just put that straight onto your sheet. Okay, so Let's think about that for a second. And I want to see these results that you come up with. So what you're doing again is that you need to find the range. You can't find the range because you don't have time, but you can use it in the vertical direction. You can take 2 times y and divide it by a. What is a again? It is 9.8 meters per second squared. And then once you find the time, then you can plug it into this formula because you've already got velocity in the x direction. And I want to see that results that you have, and I want to see your significant figures on that tomorrow. When you first come to class, I'll be checking that off. Okay, let's look at another problem. Okay, this one's going to take the full 15 minutes, so I'm going to have to talk rather quickly. An Australian football is kicked at an angle of 37 degrees with a velocity of 20 meters per second. Please find the maximum height. That's what we're going to do first. Okay, the maximum height. The maximum height is y. We can figure out the velocity in the y direction, but we can't figure out y until we do some other calculations. So look on your data, look on your table of formulas, and you should be able to see that in this column right here, there is velocity in the y direction, so we could use it because we do have 9.8. Okay, oh, we got a time problem also, so we're going to have to do some thinking, and we can find the time so we can insert it into this formula. So let's go ahead and do that. I went and manipulated the formula so that we can take the velocity in the y direction, so we're going to have to calculate that real quick with sine. Okay, and then we can 9.8 is the acceleration, so we can calculate the time. So we know how to do this, finding velocity in the y direction using our sine formula on the triangle using trig. Okay, and so when we do that, we calculate that the velocity in the y direction is 12 meters per second. Now, that's great, and we'll use that in our formula. Let me get that down there so I can use it. And we get 12 meters per second over 9.8 meters per second per second. I did that instead of meters per second squared so you could see that your answer would be in seconds. And so we get our time. So our time is 1.22 seconds, and we need to have 3 significant figures, so that's great. Okay, so now we can go and insert that into our formula. We already know what the acceleration due to gravity is, so that's great. So here, let's look at, we've got 1/2 of the acceleration due to gravity times the time that it takes to get up to the maximum height. Remember a long time ago I talked about how projectiles only, you go through half of the projectile, and this time goes up to that maximum height and is done. Okay, so if you need to have the time for the whole projectile, you'd have to double it. And anyway, so to go on further to where we're at, let's go ahead and, okay, we get 7.29 meters high is the maximum height that football will reach. Okay, that's pretty high. Anyways, the time in the, let's clean that up here. Let's find B next. B, the time in the air before it strikes the ground. So that's the full parabola. All of our formulas only go for half of a parabola, so we will have to double time, which is 1.22 seconds. We'll have to double that to get the full time that is up in the air. Okay, let's look at C. C is the horizontal distance, so we're looking for X again. Okay, X, which, and there's only one formula in that middle column of your formula sheet, and that is velocity in the X direction times time. We've got time. We've got time, and we're going to have to use the 2.44 seconds, not the 1.22. Anyways, we've got time, but we need to find that velocity in the X direction, and we'll go back to our trig functions on a triangle, and we will get that. So let's go ahead and do that. We'll have to use cosine. Okay, the cosine of 37 degrees times that 20 meters per second, and we should get about 16.0 meters per second. And I already figured out and rounded up for significant figures on that. Anyway, that is our velocity in the y direction, but that's not what it's asking. Excuse me, in the x direction. It is asking for the maximum displacement, so we've got to solve for x. Okay, so we got 16 and then the total time, and we get 39 meters. Great. Okay, so that's our answer for the maximum range. Now for D, D asks for a velocity vector at the maximum height. What would it be? Well, it's only going in the x and the y direction. In the x and the y direction, it is asking for the velocity in the x direction. In the x direction, it is asking for the maximum displacement. So we've got to solve for x. Okay, so that's our answer for the maximum range. Now for D, D asks for a velocity vector at the maximum height. What would it be? Well, it's only going in the x and the y direction. x direction, the velocity stays constant the whole time, so it'll be 16 meters per second. But if we're talking about the if we're talking about the vertical velocity, is 0 at the very top of it. So there needs to have a little bit more information there. But then there is one more e on here. The acceleration vector at the maximum height is always